Welcome to this very exciting video on the engineering analysis of Ironman suit. On this channel Synergy Files, we aim to inspire budding engineers and technologists for a better, more sustainable world. In this video, we will dissect the famous Tony Stark's exoskeleton and will look at the possibility that with the engineering knowledge and the technology available today, can the suit be made? Coming up in this video, we will analyze the suit and look at it structurally and from the point of view of energy usage. That is, how much energy is used by the suit. And we will also look at the thermal small exoskeleton that can be perhaps compared to the mech prawn biosuit in the movie District 9. The mech prawn suit was also a fascinating exoskeleton that had multiple high-tech features but lacked flight capability. In the Ironman comics, there are several iterations of the suit that the character of Tony Stark has developed over time. Suits from Mark 1 up to Mark 46 have featured in the movies. All the suits have the following capability: external armor, supersonic flight capability, hovering capability, weaponry, decoy flares. The suit can be used for multiple roles, that is, it can be used for military offense, defense, search and rescue, and espionage. So let's dive into the structural or strength aspect of the suit. The suit is wear resistant and is also capable of absorbing shocks. The material required for such properties need to be extremely hard as well as ductile. Anomalous to its name, iron would not be able to cope with such extreme requirements. In the comics, iron platinum alloy has been suggested for the suit. In real life, the only thing coming close to Ironman exoskeleton structurally would be titanium alloys. Titanium alloys are not only extremely strong in tensile strength but also lighter and therefore will provide fluidity of movement compared to any heavy material counterparts like steel. Having an outer hard material is alright to bear the brunt and provide strength against penetration. However, one must also consider that if the material is too hard, then any impact load would be passed on to the human body inside the suit. We have to remember that in automobiles, metal or composite body panels are deliberately made to crumple so to reduce the shock load that could be passed on to the human body inside the vehicle. But we cannot make an exoskeleton armor that would crumple, else its use would be just one-off. And therefore, the only way structural requirements cannot be compromised is by the use of an extremely soft material as an inner lining behind the titanium body panels. One material that is available and can be used on the inner surface is called sorbothane. Sorbothane is a synthetic material that is extremely soft and has the ability to convert shock loads into heat transfer at a molecular level. Even if one drops an egg from a high-rise building onto a bed of sorbothane, then this remarkable material is soft enough to cushion the impact and would not allow the egg to break. This technique of having an extremely hard material on the outside and a soft material on the inside is not new. It provides the best of both worlds in that the material is able to resist any penetrative load as well as any shock load. The outer hard material and the inner soft material method has been used for centuries, most notably in Japan for making samurai swords. The sword's hardness gives it the cutting edge and its penetrative power. The ductility of the sword allows it to absorb the shock loads when it strikes or is struck.